Welcome back, everyone. We are now on Chapter 2, Atoms, Molecules, and Ions. So in this chapter, there are 7 sections. We are going to start by talking about the early ideas in atomic theory, followed by the evolution of atomic theory, atomic structure and symbolism, chemical formulas, the periodic table, molecular and ionic compounds, and chemical nomenclature. So just to start off, an example of where being able to identify different elements and ions comes into play, something like a breathalyzer, or even just breath analysis, which can be done. As you can see, you've got this girl here who is blowing into this tube and this super high-tech plastic bag. But this in turn goes into an instrument that then is able to look at fragments of molecules and identify what is in her breath. So we're starting off with 2.1, Early Ideas in Atomic Theory. So here we're going to state the postulates of Dalton's atomic theory and use them to explain the laws of definite and multiple proportions. So we kind of talked about this in chapter 1, but the concept of atoms first came along by the Greek philosophers Leucippus, I forget, I know I had Jeff pronounce it in chapter 1, but I forget already, and Democritus in the 5th century BC. So we get the word atom from atomos, which is Greek for indivisible. So as time went on, Aristotle and others believed that matter consisted of the 4 quote-unquote elements: fire, earth, air, and water. But then from there, in 1807, so there really was not much work done on atoms up until 1807. Pretty recent, right? And when English schoolteacher John Dalton came up with his atomic theory. And so there are 5 postulates to this atomic theory, and a lot of it still holds true today. There's some that we are going to expand upon and change a little bit, but overall, these really held true for a very, very long time. So his first postulate was that matter is composed of exceedingly small particles called atoms. And an atom is the smallest unit of an element that can participate in a chemical change. The next was that an element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. The next was that atoms of one element differ in properties from atoms of all other elements. Number 4, a compound consists of atoms of 2 or more elements combined in a small whole number ratio. In a given compound, the number of atoms of each of its elements are always present in the same ratio. And the last one is that atoms are neither created nor are they destroyed during a chemical change, but instead they rearrange to yield a different type or types of matter. So here's just an image of a pre-1982 copper penny. I think you guys actually had a homework question last week, or it was one that I didn't put in, but copper pennies before 1980, or pennies before 1982 were basically all copper. And if you guys know, copper is very expensive, especially nowadays. Like construction sites and whatnot have to be very careful because people will break in and steal their copper wiring to sell it. So yeah. Pennies, especially back then, were worth a lot more than a cent. But when you take copper and you combine it with oxygen, you can make some different types of copper oxide. In this case, copper 2 oxide, and we'll talk about that naming stuff later. But this is a combination of copper and oxygen in a 1-to-1 ratio, where there's 1 copper for every 1 oxygen. And we'll talk more about those ratios and stuff later too. So this is just kind of showing the reaction of the copper and oxygen in this bottle. First we start off with just copper and oxygen, and then when they combine you make this copper 2 oxide. So what's great about Dalton's atomic theory is it gives us a microscopic explanation of the macroscopic properties that we've learned about. So it talks about, okay, so I left this penny out and all of a sudden it's brown. Well, why is it brown? I noticed it turned brown. But Dalton's atomic theory tells us that on the atomic scale, the microscopic scale, that what happened was that copper atoms combined with oxygen atoms to form this new compound. Now, one thing you should know is that if atoms are neither created nor are they destroyed during a chemical change, then the total mass of matter present when matter changes from one type to another stays constant. And this is called the law of conservation of matter. So if I have 10 grams of A and it combines with 2 grams of B, no matter what I make, this is a total of 12 grams. Okay, so no matter how they combine, it still should add up to 12 grams. Pretty neat, right? So the law of conservation of matter. Matter cannot be created, it can't be destroyed, it stays the same. It can change identities, okay? It changes from one type to another, but we can't just make new mass or take away mass. So here's an example looking at two different starting materials, these green spheres plus the blue. And if you look at this, this does not follow the law of conservation of matter. Okay, so we're going to look at two examples. So this one, I have 2 green and 2 blue. And those are going on to make 1 green and 1 blue. That doesn't work, right? I don't have the same amount on each side. So this does not follow. This can't happen. However, this one, I have 2 and 2. I have 4 green and 2 blue. And on this product side, I have 1, 2, 3, 4 green and 2 blue. So this one checks out. I have the same amount of everything on both sides of my reaction arrow. So another law is the law of definite proportions. The other name for this is the law of constant composition. They mean the same thing. I like constant composition better just because alliteration is kind of fun. Alliteration is awesome. There we go. So, but what this tells us is that all samples of a pure compound contain the same elements in the same proportion by mass. And Joseph Proust, French chemist, was the one who whose experiments really showed this. So, for instance, isooctane. Don't worry about what it looks like or its actual formula. It's an organic compound and organic chemistry. Nonetheless, isooctane is made of just carbon and hydrogen, but in a specific pattern. And here's 3 different samples. In sample A, the isooctane has a total of 14.82 grams of carbon and 2.78 grams of hydrogen. And if we look at the ratio of their masses, we find that it simplifies down to 5.33 grams of carbon for every 1 gram of hydrogen. Sample B has 22.33 grams of carbon and 4.19 grams of hydrogen. We take those ratios, boom. So it goes down to 5.33 grams of carbon for every 1 gram of hydrogen. There's a little, should be 22. Oh. Typos. And then sample C, 19.40 grams of carbon, 3.64 grams of hydrogen, same ratio. Constant composition. So if you have the same compound, it's going to have the same composition throughout. Same ratio of the different elements that are in that compound. Now we also have the law of multiple proportions. And so what this tells us is when you have 2 elements that can form more than 1 compound, a fixed mass of one element will react with the masses of the other element in a ratio of small whole numbers. So for instance, chlorine and copper, they can react, and there's 2 different compounds they can form. There's one where you have a solid green compound that has 0.558 grams of chlorine for every 1 gram of copper. And the other is a brown solid, which is 1.116 grams of chlorine to 1 gram of copper. So if we look at the overall ratios, we see, taking the brown solid, dividing that brown solid ratio divided by the green solid ratio, we see 2 to 1. So that means that the brown compound has twice as much copper in it as the green per gram or number of atoms. Okay. Right. So this is just showing you what these copper chlorine compounds look like, the green one versus the brown one. Neither of them are very appetizing looking, but nonetheless, this guy in B has twice as many chlorine atoms for every copper atom. So if I had some of this green copper chlorine compound, and I have 5 copper atoms and 5 chlorine atoms, then that would mean that my other compound would have to have 10 chlorines because it has twice as many chlorines for every copper. So here's another example. It's example 2.2. We're told a sample of compound A, a clear, colorless gas, is analyzed and found to have 4.27 grams of carbon and 5.69 grams of oxygen. Sample of compound B has 5.19 grams of carbon and 13.84 grams of oxygen. And we want to know if this is an example of the law of definite proportions, the law of multiple proportions, or neither. And what does this tell us about these two substances? The first thing we want to do is do their mass ratios. Okay, so the first one, we start out, we want to do, it says carbon to oxygen, but it's putting oxygen on top. So 5.69 grams of oxygen divided by 4.27 grams of carbon. And that simplifies down to 1.33 grams of oxygen for every 1 gram of carbon. Compound B, we have 13.84 grams of oxygen for every 5.19 gram of carbon. That simplifies to 2.67 grams of oxygen to 1 gram of carbon. We can already see, though, that they are different ratios, so it's not the law of definite proportions. And we put them over and we see that this is overall a 1-to-2 ratio. So compound A has half as much oxygen per carbon, or half as much oxygen per carbon as B. Okay? That's basically all we're saying here. Or we could say it has twice as much carbon per oxygen as B. So if we wanted to think of some compounds that might have this, an example would be A is carbon monoxide, and B is carbon dioxide, CO2. So if you look at that, that means A, this has half as many oxygens. So if I have if I have 2 oxygens for B, I have to have at least 2. That means I have 1 oxygen for carbon. And then if I have this 2 oxygens here and I wanted to have 2 oxygens here, I would need 2 carbons to make it the same ratio, to make it 1-to-1. Okay. Nonetheless, wouldn't really make you guys have to think of examples of compounds, because this law is just kind of a weird law. I know. Don't stress yourselves out too much with it, okay?